Hey, this is Mr. Roark. Welcome to the video review for Unit 6. In this video, we're going to look at concepts of work and energy. So we'll look at how work changes kinetic energy. It can change potential energy. We'll look at how potential energy and kinetic energy are related. And we'll look at Sloan tables all over again. Unit 6, one thing we looked at is changing energies. When you have an object that is maybe sitting still or maybe it's moving and there's some work done to it to change its energy. What we want to be able to do is predict, well, what's the object going to end up like? Basically, how fast is it going to end up going after you change its energy? And so I introduced the idea of the Sloan table. It says the initial kinetic energy plus the work done. This should be the net work, the total work. A lot of people skip that symbol because they understand it, but it really should be the total work, has to be equal to the final kinetic energy. In any situation that I give you, you're going to be able to figure out at least two of these things. Now, it could be any combination of the two things. Maybe you know how fast it's going to begin with and how fast it's going at the end, so you know the initial and the final kinetic energies. Maybe you know how much work was done and the initial kinetic energy. It doesn't matter. You'll always be able to find two of those. A big hole that people get in is just looking for numbers and not reading the problem. And maybe it says that the object, how the object starts from rest. That one most people catch. But maybe it says how far will an object slide? Well, if we're looking at how far it will slide, we're going to actually calculate how far it's going to go. It has to be stopped at the end. We want to know where is its ending point when it stops moving. And so in that case, the final kinetic energy would be zero. But in any case, you'll always be able to calculate at least two of those. So these two, the kinetic energies, are going to be based on the velocities. And that's one way to look at it. If it asks you how fast was it going to begin with, you're not going to be able to figure out the initial kinetic energy right away. That's what you're looking for. Same thing if it asks you for how fast it's going at the end. But if you know either of the velocities, you can calculate the kinetic energy. Obviously, you have to know the mass as well, but usually we're going to be looking at the velocities. The work is based on, of course, force times distance, but this has to be the net force. And a lot of people get confused there. That's why it's good to draw a force diagram and think about the forces that are working. Find the net force. I put the two forces together in whatever axis you're looking at, whether it's the vertical or the horizontal. Put any of the forces together anyway. Maybe there is only one force. But when you put those forces together and get the net force, that is what is actually going to be able to do work. You multiply that by the distance, and that has to be the work done. And then it's simply logic. I mean, if you know that you start with an initial kinetic energy of 56 joules, and you end up with a kinetic energy of, I don't know, 40 joules, well, think about it. You start with 56, you end up with 40. The work done, of course, has to be negative. The kinetic energy is decreasing. And it has to be exactly negative 16 joules. That's the only way you're going to get to 40 if you start with 56, is if you lose 16 joules. And so that means the net force would have to be negative to figure out how far it's going to go. So all these energy questions, these changing energy questions, can be done by thinking about this Sloan table and thinking about the changes in kinetic energy and how they affect an object's motion. Unit 6 equations. So in Unit 6, we had a few equations. We had this one, this one, this one, this one, and this one. So actually 5 total equations. Let's look at the first one. KE equals 1/2 m times v squared. This is the kinetic energy equation. It lets you calculate the amount of energy an object has because of its movement based on its mass and its velocity. This isn't too hard of an equation to use, except you have to remember that the velocity here is squared. So when you put it in to find the energy, you got to make sure you square the velocity, take half the mass, and then multiply. Remember your order of operation. But really, the way we want to use this is if we know how much kinetic energy an object has, we should be able to calculate the velocity. That's really how this is useful. So we know, okay, an object has, say, 500 joules of kinetic energy, and its mass is 10 kilograms, something like that. We should be able to find its velocity from that information. The one thing that students get tripped up on sometimes is forgetting that square. So when you solve this, let's actually do that. 500 equals 1/2 times 10 times b squared. So half of 10 would be 5, and then we're going to divide by 5 over here, and we actually get 100 equals b squared. And a lot of students stop right there and realize this doesn't tell us the velocity, it tells us the velocity as a square. So to cancel this out, we actually have to take the square root of each side. And we get that the actual velocity here is the square root of 100, which is 10 meters per second. So that's really the most useful way to use this equation. The next equation is the work equation, and it tells us that work is equal to force times the distance. This is a pretty simple equation to use. Sometimes you're going to have to, based on the work done, if you know the work done, you're going to have to calculate how far the object moves or how much force was causing that work to be done. This is a fairly straightforward equation, but we also need to remember that work is also equal to the change in kinetic energy. And that's important to understand. Now, that's not an actual equation on here, but it's a theorem. It's called the work energy theorem. And we use that in conjunction with the actual kinetic energies of an object to figure out what's going on. So basically, when you calculate the amount of work done to an object here, that's how much the energy of that object changes. Now, if you have a positive force pushing in the direction that the object is already going in or is going to move in, then the work done is going to be positive, and the change in kinetic energy is going to be positive. The object is going to gain that kinetic energy. If the force here is negative, and that's going to happen if the net force is in the opposite direction that the object is moving, then that is going to take energy away. And so the work done is going to be negative, and the change in kinetic energy is going to be negative. And in that case, that net negative force is actually going to slow the object down. The next equation that we have is the potential energy equation. So here we have GPE equals weight times height. Gravitational potential energy is equal to an object's weight times how high it is above the ground. The gravitational potential energy, remember, is based on how much work gravity is going to do as the thing falls. The one thing that you really got to be careful about is that this is weight, not mass. In a problem, it's just going to tell you what the mass is. It'll say, oh, a 10-kilogram object is so far above the ground. But you have to calculate the weight. So moving back to an equation we used in another chapter, weight equals the mass times the acceleration due to gravity. You've got to use that and calculate the actual weight of an object based on the mass and the acceleration due to gravity, which is 9.8. So you take the mass times 9.8, and then we can put that into the equation as the weight and figure out what the gravitational potential energy is based on the height. Okay, the next equation here is ME equals GPE plus KE. And this is the equation for mechanical energy. The mechanical energy of an object just basically describes what the total amount of energy it has, as long as there's no forces other than gravity that are working on it. So it's going to be equal to the potential energy and the kinetic energy added together. We usually see this in a case of an object that is dropped. We can use it for roller coasters as well, though. So for a roller coaster, it starts with a certain amount of potential energy. As it goes down, that gets converted into kinetic energy. And then as it goes back up, it'll get converted back into potential energy. But during that whole time, as long as there's no significant friction, these two things added together should always equal the same amount. So this mechanical energy, as you're dropping the object or as it's going up and down the roller coaster, if there's no significant friction, there's no energy losses, then that mechanical energy should be the same all the way down. And so at any point, if you know the potential energy based on the height of an object, and we can usually calculate that, and the mechanical energy has to be a certain amount, well, then we can just subtract to find the kinetic energy. And why would we want to do that? Because if we know the kinetic energy, then we can use the kinetic energy equation and figure out how fast that object is going. So in this case, usually what you're going to do is, okay, it starts out with a certain amount of potential energy, and it starts out with 0 kinetic energy because it's dropped, or it actually could start with some kinetic energy. But the point is, you would figure out those starting amounts. That has to be the total amount of mechanical energy, and as long as there's no friction, that shouldn't change. And this is useful for an object that is dropped, or like I said, a roller coaster, a ball going on a ramp, whatever, as long as there's no friction. And if you find the height, or the potential energy based on the height, then you can find the kinetic energy and figure out how fast it's going at that point. And then the final equation for Unit 6 is pretty simple. Power is equal to the change in energy divided by the time. Now, a lot of people in Unit 6 got this mixed up with momentum. Remember, momentum is a lowercase p, but also momentum doesn't really have anything to do with energy transfers. And here, delta is change, remember, so this is the change in energy divided by the time. It basically just tells you how fast the energy can change, how quickly you can get energy from one sort into another. So for example, from electrical energy into heat energy or into light energy. But usually the way we're going to see it is in the terms of work, because remember, work equals a change in kinetic energy. That's a type of energy change. That means if we want to figure out the power for an object and we know how much work is done, we can simply put work in to that equation, divide by the amount of time, and figure out what the power is. In some cases, what we want to do is, based on the power, we want to figure out how much the energy changes based on the amount of time that it takes. And so we'll multiply the power by the time to find that.